So finished the last video with the startling revelation that I'd forgotten to implement loads of instructions, namely the subtract with carry instructions. Well, most of them. I'd actually implemented absolute. And I went back and watched the video and I said, and in the next video, I'll implement all the other addressing modes, which I promptly didn't do. So they are completely missing. And that is why the test program, this one, by class 2M5, the functional test, and it's why it fails, and I can run it now, and it gets to here and says, yeah, instruction E5 isn't handled, and that turns out to be this one, subtract with carry zero page. In fact, I've not done any of them except absolute. That's the only one I've implemented. So all the code's pretty much written for subtract with carry. I just haven't done the rest of the addressing modes. Yeah, so I've got like a bunch of tests for just the absolute mode, and really they just need refactoring out so that they can be done for the other ones as well. So, and we can even like kind of reuse the test. Like what I'm doing with the subtract with carry is just basically for the absolute one, I've passed in like this enum for add, and then I just changed the instruction. And at the end of the day, because I'm passing in the test data, this whole thing should just work. But I just didn't do that. So maybe I'll do them in the order that they are failing in. So zero page, I'll do zero page first. So let's just do that. So this is back to these old tests basically. The first thing I want to do is in the zero page, so it's called ADC absolute, but actually it can do add or subtract if I just pass in the value and change the opcode. So we just don't want to rewrite tons of code in these add or subtract tests. So if I find the zero page version of this, yeah, so we've got an ADC zero page. So I'll pass in this enum value, which is the just to change whether we do add or subtract on this, and then I'll do the very similar thing that we did up here, which is just change the operation that we're going to do, which is here. So if we're doing add, we do the zero page one, otherwise we do SBC zero page. Let's get rid of that. I think that's right. And then we can just make a version of this where we actually pass in the subtract version to that. So that's just basically refactored that code where we do the add with carry test, and we've made it into a subtract with carry test as well, just by changing the operation. And we can do that because we're passing in the test data and we're not actually assuming any of it in here. So that should be fine. I can now go and implement this thing, which I forgot to do. Like that. Yeah. And then the next thing I need to do is actually duplicate all these add with carry tests here. I think we've got 6 of them or something like that. Or subtract with carry, sorry. Yeah, that's one. That's one. It's quite a few. So I'm going to copy all these. This is the SBC absolute tests here. If I go down here, these are going to be SBC zero page. That was the one, wasn't it? Yeah, zero page. So duplicate all the tests, and basically we need to change that to change this test here. Call that, call that, call that. So yeah, we're just changing the test function. And just need to change the name of this. Let's call it zero page. So this isn't really going to be super complicated because I'm just refactoring tests that I've already written so that they can work on the zero page version of it. So that should compile. And I wonder, we should still get instruction not handled when we write code because we haven't written it yet. Oh yeah, all those are failing as well actually. And the test program's failing as well. That's fine, I think. Let's just go in and fix that now then. So all we need to do to fix this is take the SBC absolute code and do the zero page version, and it's the addressing mode zero page. And everything else stays the same. And that should fix all those tests, I hope. Which it does, but our program still crashes. The test program is still not working. But I think we'll find that's because if that has worked, it's passed on to a new instruction that doesn't work. And let's just see if that's true. E9, there you go. So immediate mode is also, that could be the next thing. That shows that we did actually also, not only were the unit tests working, but we're actually passing the tests in that test program, and that's progressing a bit further as well now. So maybe I should do that one next. So this is going to be really very much the same thing here. Let's go find the add with carry tests for apps. Immediate mode, isn't it? Immediate. Where are you? Immediate. There we are. So we're going to pass in the operation that we want to do. And then let's copy that other bit. A lot of copy and pasting in this episode here, I'm afraid. It's mostly going to be copy and pasting. So instead of actually doing that operation, so this is just ADC, and this one's just SBC. That's just the basic immediate mode version of that. Need to go and implement that. And this one was E9. Can't believe I forgot to do all these, it's just ridiculous. And then same thing again. Oh, wait a minute, I've got to call this as well. So I'll make a version of this. So it's going to call test SBC Immediate. So now we've got a version, we can just recall the same test, and we're going to go down here and we're going to do the same thing again. We're going to duplicate these tests that we simplified as much as we could really. We could simplify them a bit more, but I'm not sure if it's worth it. And we're going to make the SBC Immediate tests for that. So, same thing again. We call the different test, which is, it's passing, so it's basically doing the same subtraction, but we are changing the addressing mode. And then I need to just rename all these tests again. And same thing again. We got 9 more. Well, we got 8. Basically 8 tests that don't work, and that our test program doesn't run. So now we can go and implement that. Where are you, SBC? So again, we take that. This time it's just raw SBC, and this one just fetches a byte. Actually, it's very much like this one. You fetch a byte and then you just do SBC on it. So that's the immediate mode version, just fetches the next byte in the program. And there we go. And that looks like that passed, and we're probably back to the next instruction. Let's just see. Yeah, F5. There you go, 0. They're actually almost going in the order that's in this here. So we've done immediate, done zero page, and now next one's zero page X. So I'm going to go to warp speed for this because it's just going to be me doing the same thing over and over again. You've just seen me do it twice. So I'm just going to be doing that again for zero page X, absolute Y, indirect X, and indirect Y. Same thing quite a few times. So it looks like now I've implemented all those, I've basically gone through and done the other addressing modes. The test program is no longer saying it's found an invalid instruction, it's now halting, which remember is what it does. It will halt on success or failure. So it just holds on the program counter at the point where either the error or the success happens. So that means we have progressed past the subtract with carry test, or we're stuck inside them somewhere because we've done them wrong. But it seemed to be progressing past each instruction as it went. So that's probably a good sign. So the next question, I suppose, is what's gone wrong? Or what's gone right? We'll have to have a look. So if I pause here, and let's see where we are at. What are we doing? Oh, we're doing something. Oh, we're stuck. We're inside an add with carry here. That's interesting. I wasn't expecting that. Is that really what's happening here? Maybe add with carry isn't working. 08. Oh no, it's something's going on here. Is it actually progressing? Three 360. It's. Oh, does this mean it's actually working and it's going? Is it looping around the whole program? Is this? Oh, don't know. I don't know what's happening here because it looks like it's not stuck. It says it will halt on the program counter on success though. So this doesn't seem right that it's. No, it is stuck. We are stuck at 336E. So let's have a look at what that is. And this is the symbols file for it. What is the instruction it's doing? Oh. Yeah, we're definitely stuck there. 336D, is that there? Test passed, no errors. Are you kidding me? Oh, stop it. Visual Studio Code. If you got here, everything went well. Oh my word. That might actually mean that we've passed, well, except the decimal test, but we've passed all the tests in this program. So yeah, I'm quite happy about that. We've managed to, I mean, it doesn't mean it's still fully working, but we've made it through this entire program. In fact, this is the program here. So we made it through this entire program and we've made it to the end. It seems like that was the last thing to do, is that we were missing the subtract with carry tests. So that's definitely, yeah, look at all this that we made it through. So this apparently tests all the addressing mode of all the instructions. Like I said, we haven't implemented decimal mode. I've turned that off. But other than that, this is like, you know, I'm getting a lot more confident that there's something here that works now. So that's really good. So yeah, that's where we're stuck. We're stuck on the success. I don't know what the last thing it did was though. But that's really good news. That's a good thing. Was there some other things to do though at the moment? Yeah, there was one other thing actually. So somebody in the comments, I'm going to find their name now, Sam said, it was when I was doing conditional branches, because one of the important things about this test program is it's testing all the instructions and they're all working, they're doing the right thing. But what it's not testing is whether I'm emulating the correct number of cycles, because it doesn't know anything about cycles. It just executes code and then sees what happens. It doesn't know that a single instruction took 10 cycles, 100 or 1,000,000, but we have to take account for that in our program. And that's one of the problems with with this kind of program, is it's still not necessarily fully implemented correctly, because we have to know that. Now I've got tests that I hope are testing all that, but I still could be wrong. But someone has pointed out, when I was doing conditional branches, so it was relative addressing mode. So he said, are you sure that in the case that if branch instruction leads to another page, it consumes 5 cycles but not 4? In my opinion, the doc says 2 cycles plus 1 branch, or plus 2 if it goes to a new page. So 2, it says so 2 or 3 or 4. But I think he's saying that's what I did. Anyway, his point is that I read this as when you're doing the relative addressing, it takes 2 cycles, but you have to take an extra 1 if it succeeds, and then an extra 2 if it's to a new page. So that would be 3. But actually it's not. It's 2. It's either 2 plus 1 or it's 2 plus 2. It's not 2 plus 1 plus 2. God, there's no easy way to say that, is there? Anyway, I'll look at the code. Let's just look at the code for BQ. It's in here. Wow, it's taking its time to find that. Yeah, so I subtract 1 if the branch succeeds, and then I subtract 2 more if we change the page. But that's not the case. I think they're saying is what actually happens is if it succeeds, you take 1, and then you'll take another 1 if the page changes. So yeah, I think I'm reading that wrong, and basically this is wrong. So I'm not going to change the code. What I'm going to do, I'm going to change the tests. I think it's only 1 actually I've got for, is it page? BQ can branch forward into a new page when 0 page is set. So I think this is not 5 cycles. I think it's 4. Or Ander Sam says he thinks it's 4, and I agree. I think I read that wrong. Let's see if there's any other tests in here that go. Oh, it's just the 1 that goes into a new page. So I only did the 1 test for a new page, but I think, yeah, I think that was wrong. So let's just have a look at that. Oh, I need to take my test program out now because otherwise the test program never finishes even if it's successful. So I need to take this out. I'll completely remove this. So that can't stay in, unfortunately, because it's just not possible. But it's helped us write tests that can make this pass. So there you go. BQ can branch forward into a new page when 0 is set. So that one will be failing on these cycles being wrong. So it takes 1 if it succeeds, and then it takes an extra 1 if the page changes. I believe it's as simple as that. And I think the reason is because when the page changes, it just has to adjust 1 more byte. So it's adjusting the high byte of an address, I think that's what it's doing, which would make sense that it's only got 1 more byte to change, so it only needs 1 more cycle to do it. So that puts us back into finished test, and we ended up with 361 tests. So yeah, so hopefully that's a bit more correct now as well. So I don't know where to go next with this. We've got, I think, a working 6502 emulator. We could call it there, I don't know. I mean, depends what we want to do with this. I suppose really we want to be able to actually visualize what this thing is doing. There's probably some things that we've missed, like decimal mode. I mean, maybe the thing to do here is to update the Readme file. So, as of, this is the 11th month, 2020, the year that would not end. What we want to do is we will put in some notes about what we've got and what we haven't. So we've got all instructions emulated. So we've got will succeed if decimal mode is disabled. So decimal mode is not handled. So that's one thing. So decimal mode is binary coded decimal, and that's not implemented. We've got a note about jump. In fact, it's right on the screen there. Jump absolute see notes about bug in 6502 if correct emulation. Because yeah, it's one thing just making this work, but then it's another thing actually properly emulating an actual 6502, including all of its bugs. So counting cycles, this is another thing that I think I might do. Counting cycles individually, let's call it that. Individually for each part of an instruction is cumbersome and probably should just deduct the correct number. Because one of the things I thought when I started this is the reason I'm passing these cycles around everywhere is because I actually want each part of the program to deduct the cycles that it would have deducted for doing the thing it's doing. Like write byte is deducting a cycle for writing a byte. The problem is it relies on a lot of knowledge about how the actual 6502 works and whether, you know, this particular write byte takes what, and does it really take a cycle? And the answer is I don't know. And I wasn't actually sure when I wrote this whether an interrupt for the processor could actually stop an instruction halfway, but I've since read in the 6502 datasheet that it doesn't. So if this instruction starts executing and you get like to here and you're only halfway through and an interrupt is issued to the processor, it will finish this instruction before actioning on the interrupt. So you'll never be halfway through an instruction and be stopped. It never has to be backtracked or anything like that. That's what the datasheet says anyway. So really you could just like deduct the cycles at the end, but then you've got the slight problem that some of them take different amounts. But it might be easier then, because then I wouldn't have to keep passing in cycles. I could just have a lookup table and look up the cycles to deduct, and it might make this a bit easier. So that's one thing. So another thing, mentioning interrupts, there is no way to issue an interrupt. Yeah, so that's another thing, is that even though we've done all the instructions, like there is a pin on the processor that says interrupt me now, and we stop what we're doing, and we haven't provided a function to do that. So that's one thing. So that's something else. And another thing is there are no hooks for debugging, or yeah, let's just say debugging. So one of the things is you might want to do is we could put in a hook, say, and a hook just being a function that is allowed to be implemented by someone who is using this library, that you could have a hook here at the end and it says after every instruction, if you've implemented this function, we can call it, and you could use that to create a disassembler or look at the memory at that point. So basically you could halt the execution of the CPU and then only carry on when someone else allows. So that'd be useful for debugging. So we don't have that. There are no asserts. There are no asserts if you write memory outside of the bounds. I think that's true. So if I look in here, where's memory? Yeah, assert here. So yeah, if you basically wrote to an address that was outside of the size of this data, it won't even assert at the moment, it'll just overwrite memory. So that's the thing. It will overwrite memory. Another thing, illegal opcodes are not implemented. Sorry, I should clarify that. There's all 6502 legal opcodes emulated. So those are just the ones that the processor actually says it will do. Illegal opcodes are not implemented. The CPU, the program will throw an exception. So if you issued an opcode that we didn't understand, you get that sorry, instruction not implemented, and it throws an exception. And there are some opcodes out there that the 6502 doesn't actually support, but in some 6502 implementations did actually do something. And that's another reason why you might try and run a program and it doesn't work, because you've got to do something that the CPU wasn't supposed to do. There's definitely that. Anything else? No, I think that's it. So there possibly might be a next video. I might attack some of these. I'm very grateful to Klaus 2 and 5 for making this program, because I mean, regardless of whether this is even a valid functional test program or not, the point is that it was compiled with a separate compiler and it did run all the way through to a certain point. So clearly the fact that it isn't crashing and it isn't doing illegal opcodes and stuff like that is a good sign. But this looked like it tested a lot, because it did find a lot of programs, mostly in the break and the way I was pushing on values onto the stack and stuff like that. This has been a big help, and the fact that I know that I'm not missing any opcodes now, so that's a good sign. So I think if I do any more videos, I'd probably like to get rid of this cycle counting stuff. I'd like to put some debugging, some hooks for debugging in, and then we can actually print some stuff on the screen. We could single step the program, the virtual program in the 6502. We need to be able to issue interrupts if we want this to work. We need to get decimal mode fixed, because an actual 6502 program that wants that wouldn't work. And then you can just really point out, like, what did we learn from this? What did we learn from making an emulator like this? So the first thing is, a program is just a big bunch of bytes. It's just a big array of bytes. There we go. That is what a program is. It's all it is. You just feed in a massive bunch of bytes, and the CPU reads those bytes and starts executing them. And that's really all it does. That's the same in a modern processor, although they're more complicated. It's the same here as it was 40 whatever years ago. It's the same now. A program is just a giant bunch of bytes that you feed to the processor. That's what you need to know. This is another thing I've learned. Writing a CPU emulator is time consuming, because you can see here that again, it wasn't a huge amount of time, but this is like the simplest processor I could really think of. And this has taken 32 videos to get to the point where it's not really fully working. And you couldn't really use this. Well, you could maybe use this, but it's basically taken a lot of work. And the original video I mentioned from One Lone Coder at the start of this saying, I think I mentioned it in the description, saying if you want to see somebody implement this, look at their video. But he only did an hour-long video, and he'd already written the emulator. But he did say at the end, if you watch the video to the end, that it takes a long time, and it took him a long time to do this. So I thought I'd actually do the whole thing on video, and then you can actually see all the work that went from, I just went from void main to this emulator, and it's taken 32 videos and quite a bit of debugging and learning all about the processor and stuff like that. What else did we learn? Some features are undocumented. So there you go. So that was like, we had documentation for when you break, you write all the stuff to the stack, but it turns out actually you write some weird bytes and things like that in there as well. So you have to be aware of that. I think I learned that emulating a CPU is harder than you think, because you have to emulate things you got for free. Like the clock, for instance. So the clock when I'm talking about the clock in a CPU, I'm talking about the thing that pulses, that synchronizes all the operations. So it's just a on, off, on, off, on, off. And then things in the CPU do things on those clock cycles, so they make sure that they're not overwriting the other work that the other hardware might be doing at the same time. You get that for free well, you don't get it free, but you get it for free in a real piece of hardware, because the clock just pulses and the thing just works. But here, I have to count the clock cycles because I need the clock, but no one's keeping track of it for me. So I've had to make the clock and pass it around and count the cycles. So it's definitely, it's definitely harder than you think. And I would say that writing unit tests for the CPU was a good idea, and I wrote them before I wrote the code, so everything that's in here is driven from this. And I'd also like to say that this isn't the only way you could write one of these. This is a giant switch statement way, but you could do different things like decoding the opcodes and stuff like that. In fact, if you try to emulate something like the Motorola 68000, I think you would find that the way I've written this one with this massive switch statement just wouldn't work for you, because it's got way more versions of the instructions. So like here, I'm just like treating each one as an individual instruction, but the addressing mode and stuff is encoded inside these bits here. So you could actually just like decode the addressing mode and then work out what to do on the instruction. So that's definitely another way of doing it. Now, I don't think you have to do that for the 6502 and because it's only got 150 instructions. But if I tried to do that on the Motorola 68000, there would be thousands and thousands of instructions probably. There's like, some of them have got like one instruction where one of the registers is encoded into the opcode, or is it two of the registers? But there's two sets of registers and there's 8 each. So just one instruction, like, or one thing like add, can have like 64 different versions of it. So clearly, if you wanted to do the 68000 emulator, you wouldn't be able to attack it like this. You'd have to go for more like a decoding the opcode and then working out what to do. I've not done that on this one because I didn't think it was necessary, but you could do it on this one as well. So that's worth knowing. That big switch statement works for small instruction set processors, probably not for big ones. And it's probably worth noting that if you took a modern processor and you tried to do it on that, you would be overwhelmed by the number of instructions that they have. It's just unbelievable what goes on these days. So, but essentially it's the same stuff, but they just have more instructions, more registers and that kind of thing, you know, and SIMD and all that kind of stuff going on. So that's really good. So if I do come back to this, I think I'd like to, debugging hooks and get like a UI program on the screen so you could see it. And even then, in the One Line Coder video, he'd already got to that point by the end of the video where he had a disassembler and something on the screen and a debugger, and I've not got any of that, and I've done 32 videos. So yeah, there is no disassembler or UI. This is just the CPU emulator and unit tests. But I think having the unit tests like this is really cool. Like, there's my 361 tests passed. I think that's a really cool thing to have, I think. Assuming you've written all the tests right. I mean, you could have got some of these wrong, but we don't know that. If we do want to do the cycle counting and change that, that'll be really cool because the tests themselves won't actually change, I think. The test should stay exactly the same. It should still expect to come in and spit out the number of cycles it took. I can just change internally how it does the cycle counting so that I don't have to keep passing this around, and that would work. But again, this is known to be working right now, so it's not as pretty as it might be, but it does work. But I think you could get rid of a lot of this cycle stuff and possibly do a lookup table. Possibly. Whether it's worth it is another matter. It's probably not worth it because this isn't totally unreadable. Some of these have only got 2 parameters, so it's not like that's really bad. Yeah. So this might be the last video, but if anybody wants to comment, and if anyone got to episode 32 and to the end of the video and is listening to this, if you do want some more, you've got to ask for it. But it's like, I'll just get one comment saying, hey, can I have another video? So yeah, maybe I'll do some of this. Maybe I'll go in and do decimal mode. That might be a nice place to continue on this, but it definitely needs a bit more work if it wanted to be used. But I'd say this is reasonably functional. So I might catch you in the next one.